All right, so we're recording now. We'll officially begin. Before we, pick up where we left off, talking about factors of safety and allowable stress on Friday, a couple of piece of information to pass along. Um, Make sure you're aware of. So it's still looking like right now my best guess. Test number one will be a week from today, Monday, the 15th, and it will be at 11 a.m. So my regular class time is when we will take the test. And also pass this information along to you. After class today, I can't give you a specific time, but sometime not too long after we finish class, I'm going to send you out a couple of emails. So sometime middle afternoon or so, make sure you check your email. And what these two emails are going to include is there'll be one email with some information regarding Honor Lock. Some of that you may already know or have seen before, but I want to provide you with all the information that I have to make sure everybody is familiar and comfortable using Honor Lock as you can be before the test on Monday. So they'll Friday afternoon, I went in and enabled it's like a demo quiz in Canvas that's strictly just to get you familiar with the Honor Lock process. Um, I'll tell you about that in the email. There's also provide you with some links to some other sources of information and some frequently asked questions and so on and so forth. So one email will contain some information about Honor Lock, and then I'll send another email that's got more detailed, specific information about the process and the procedure for taking the test, exactly how that will go. And again, this will all be in the email, but one thing I'll mention while I'm thinking about it is you will have to have the capability to scan your work, create a PDF, and email that back to me. And I'll provide you with some suggestions if you don't have a scanner that will do that. And so that's what the other email will be. I really want to encourage you, and part of the reason I'm telling you this is make sure you look at those emails sometime today, tonight, tomorrow morning, before we meet class again at 11 tomorrow. And then if you have any questions about the information that I sent out in those emails, then we can try to answer those questions during class tomorrow at 11. Okay? So, got that out of the way. We were in section 1.6 is where we were, I reckon, ended on Friday. And just sort of, quick review what a factor of safety is you take whatever the failure stress is and divide by whatever the actual stress is, that gives you the factor of safety. And come on, it's not want to focus for me. And again, this could be the failure stress, could be the yield stress of the material or the ultimate stress of the material, either one. And where we're headed is from that, if we want to actually design this structure, we can get what the allowable stress is, which is the maximum stress this structure is allowed to see by, again, just solving for sigma here. So it would be whatever the failure stress is divided by that factor of safety. And I did this for normal stress, but the same would be true for shear stress. If you took whatever the failure shear stress was and divided by the actual shear stress, that would give you the factor of safety on shear. And likewise, if we're trying to design this structure, we need to know what that allowable stress is. We get it by taking the whatever the failure stress is divided by the factor of safety. All right. Now, that's basically where we stopped on Friday. And so the first thing I want to do before we actually get into designing a structure here is kind of give you an idea, a feel for what are typical factors of safety that are used out there in the real world. I think I may have mentioned this Friday, but wherever you go to work, it's going to have requirements. And again, there is no national standard that everybody uses. It's individual companies require different things. Now, there are a couple things that are used widely across the country. One of these, my civil engineers might have seen this before. So let me ask the question. Any of my civil engineers out there ever heard of AISC? You can speak up or reply with the chat if any of you have seen or know what those letters stand for. Nobody wants to speak up, or nobody wants to take a guess, huh? All right, well, if you're a civil engineer and you haven't seen this before, I can promise you almost 100% you're going to see this sometime, probably soon. The AISC, it's American Institute of Steel Construction. It's basically what most, say, any kind of steel structure, building, all these buildings on campus were built to satisfy the requirements in this American Institute of Steel Construction. Now, I don't want to pick on the civil engineers, but they tend to do things a little different in many areas. One being factors of safety. You'll see in the AISC manual, it doesn't most of the time give you a direct factor of safety. It has lots of tables and charts and graphs and things that you use to determine what size beam, for example, you need. But if you back out and figure out what that factor of safety is that table gives you, it generally comes out to be about 1.5 on yield. It's almost always based in the AISC manual, almost always based on yield, and it's usually somewhere around 1.5. And so that's what these, like I said, this building, the beams, steel columns in this building, basically designed to take 1.5 times what the actual load is expected to see before you would have any permanent deformation. Remember, we said the yield stress is where you get permanent deformation. Again, specific individual companies, I don't know. I can only give you some examples of where I personally worked. So I can give you some examples there. I worked at NASA for about 5.5 years. And for most, if it's just some kind of general structure, again, this would be, we're talking about non-flight. It's like some kind of test stand or a piece of equipment you're going to use to test a piece of flight hardware, or pressure vessels, piping systems, things like that, just general structures. NASA requires a factor of safety on yield of 2.0 and a factor of safety on the ultimate strength of 3.0. Again, whichever one of those is more restrictive, that's what you would have to meet. If you're working at NASA, any piece of structure that they design or build is required to meet those factors of safety. Any contractor that's got a contract to build something for NASA has to meet those factors of safety. Now, if we get into like lifting or like hoisting equipment, something like I can't spell equipment, like an overhead crane. You see, you're going to pick up a space shuttle or a solid rocket motor and pick it up and move it from one place to another. Factors of safety on that type of equipment are higher, which you would think kind of makes sense. If you're picking something up and moving it around, you've got the possibility, if it fails, not only is the piece of equipment going to fall and hit the ground and break, and you just lost a $50 million piece of flight hardware, but whatever it falls on and hits is probably also going to be destroyed, like a person. And so you're required to be extra safe if whatever the structure is used to pick something up or lift something. For that type of equipment, we had to have a factor of safety on yield of 3.0, and on the ultimate strength it had to be 5.0. So, for example, if you're at NASA and you see this overhead crane and it says max load 2 tons, that crane was designed to take 10 tons before it actually break. Right, so it's way over designed. This is for safety purposes, safety reasons. Also, any kind of lifting or hoisting equipment has to be proof tested. So before you could actually use that overhead crane, you would have to pick up twice what the design load is and demonstrate that it's not going to break. So anyway, again, this is things that I have personal knowledge of. That's why I can pass it along. But if you go to work at I don't know, General Motors or Boeing or whatever other company, they're going to have their own requirements, and they may be similar, maybe higher, maybe lower than these. I don't know. That's why I said it's not a standard. Across the country, everybody does the same thing. Now, when you get, again, all of this is non-flight. When you get to flight hardware, your first inclination might be, okay, well, I got a general structure. When I pick something up, my factor of safety go up and get higher. Well, if I'm going to fly something, it's definitely getting picked up off the ground. And you would think that those factors of safety might, be higher than what it is for just general structures. But in fact, it is exactly the opposite. The factors of safety go way down if you're talking about flight hardware. And I posed a question to civil engineers a minute ago. Didn't have anybody take that up. But anybody, if you've got an idea of why the factors of safety for flight hardware go down and decrease as opposed to increasing to make it safer. I know if I have a aerospace engineer out there, would surely hope maybe one of you might offer an opinion of why that is.
Would it be because the aircraft slowly gets lighter, like as fuel is burned?
No. You were kind of close to the idea, but it's not that the weight gets lighter as it flies because the fuel's burned. Anybody else want to offer an opinion or a guess? Well, generally speaking, as factors of safety go up and get larger, the structure gets bigger, right? If it's stronger, typically you got a bigger structure. And if the structure gets bigger, it weighs more. And when you're talking about flying something, weight is so critical. You could design a space shuttle or a rocket that you could pretty much 100% guarantee it's going to be safe every time. But it would be so heavy, you would never get off the ground. You couldn't launch. Right? So that's why you see factor safety go way down. And I actually copied one of the things I actually found that I actually brought with me. This is it's a page out of the MSFC. That's the Marshall Space Flight Center Handbook 505. It's this big old thick 3-ring binder. It's got all these requirements in it. And if you look at, again, here we're talking about metallic flight structures. Well, if it's manned, if it's just analyzed, it's 1.5 on yield and 2 on ultimate. But if you test it as well as analyze it, you can even go lower. You can go down to like 1.1 on yield and 1.4 on ultimate. That's a big decrease from 2 and 3. And again, the reason for that is weight. The structure's got to be as light as possible. Now, if you go unmanned, you can even take it down if you do analysis and test, where you can get down to 1.25 on ultimate. But those yield stress of 1.1, that means, just take for example, say the space shuttle when it flew before it got canceled. You were right at the yield strength of that material. You do not have a whole lot of margin for error. Your structure is designed to be basically right at the yield strength. So if you have any kind of unexpected load that you weren't counting on, it doesn't take a whole lot to cause some permanent damage. And when you start talking about the ultimate of 1.25, there's not a whole lot of margin there either. You're basically, if you see any kind of significant load change, you're going to have failure. Structure's going to come apart. Anyway, so that's just to give you some ideas of what's out there. Like say I mentioned like General Motors or whatever. I guarantee your car is not designed to factors of safety that low, because weight's not so critical. You make the trade-off. We'll make it a little heavier, make it safer. But anything that flies, got to be light. All right. Any kind of just general questions related to like factors of safety before we move along? All right. So next thing wanted to talk about, there's another stress that we have not encountered yet, but before we get to this is in the next section, is 1.7, is we're going to talk about design. So basically we're going to again go backwards. We're going to be given an allowable stress, or we'll be given what the yield stress, ultimate stress, and a factor of safety, and determine what our allowable stress is. And from that, we'll design how big does the structure have to be. But as I said, there's one stress we haven't mentioned, and I'm not real sure why he waited and put it in this section. But just a couple minutes, I'm going to talk about something called bearing stress. Now, we've discussed normal stress, we've discussed shear stress. This is a third different kind of stress. And this is the stress that's due to the compressive forces of two surfaces. They're pressed together. So, first, description there, it sounds a lot like a compressive normal stress. And to some extent it is, but the difference being, if you've got a solid bar that's in compression, if you go out there and look at some internal cross section, it's going to have a compressive normal stress, P over A. And that material will yield at whatever the yield stress of that material is. But here we've got two different structures that are actually being pressed together, right? We're not talking about an internal force in one structure. For example, I don't know how well this will turn out if I can draw a 3D picture here. You see this a lot, civil engineers do when you start talking about foundations. You've got, the weight of some building pressing down on a foundation. But say if you took, I don't know, this probably won't turn out too good. And pretend like this is hidden back here. So say I've got this rectangular bar or column, and these two things, they're not attached. Right? This rectangular bar here is just sitting on top of that plate, and I push down on that bar. Well, that is going to exert this pressure over this, we'll call it AB for the bearing. So if you look at what just the plate is seeing, again, this being this what we call the bearing area, you're going to see this compressive pressure, if you will, pushing down on that area of the plate, and the bearing stress, we'll do sigma B, is whatever that force is that's pushing down on that area, and that resultant force here would be whatever P is. And so it's P over A, just like it was, before with normal stress. But really the difference is the effect on the material is different. Again, the compressive stress in this bar is going to be exactly the same, P over A, and that bar would yield at whatever the yield strength of that material of the bar is. The bearing stress on this plate that it's pushing on is going to be the same, but it's not going to yield at that same strength. So typically, if I can spell typically, called the bearing stress, BR, so maybe we'll do BR here, is going to be greater than whatever the yield stress is. So that plate that bar is pushing on, that material is not going to have permanent deformation at the yield stress. It's going to not experience permanent deformation until that stress reaches what the bearing strength of that material is, which is much higher typically than the yield strength. And so you see this again a lot if you've got like, something like this where one piece is just pushing against another one. Another common place you see this is, we talked the other day about we had a bolt. Well, that bolt is going to be pushing against the hole in the plate. Like if you take a plate and cut a hole in it and you put a bolt through there, well, that bolt's going to be pushing against the inside of that bolt hole. And that stress is a bearing stress and will fail at a higher stress than just normal yield stress will be. So we're not going to see this a lot. In fact, we get past this section, I don't remember if there are any other problems related to bearing stress in the book, but I'm pretty sure there's one or two maybe that I assign. And I'm sure there's an example that asks for bearing stress or involves bearing stress. All right, so any questions about what bearing stress is? All right, well, we're about ready then to work a problem. Again, what we're going to do is, we're going to get our allowable stress by taking whatever our failure stress is, divide it by whatever factor of safety that we're required. And then from that, we're going to use, we know the allowable stress, and normal stress in this case, is P over A. And then we're going to use that to get, what the size of that structure is. Right? And the same thing would fall for shear stress as well. If you've got an allowable factor of safety, you can get the allowable shear stress. Once you know what the allowable stress is, then tau allowable is V over A, and you use that to write it down. So we use that to get whatever the size is. So the factor of safety gives us allowable stress. And then our formulas that we've been using before, instead of solving for stress, we're going to be solving for the size. Right? All right, so any questions before we work a problem? All right, then let's see if we can do this one. I'll point out there are several good examples in the book. I certainly encourage you to take a look at those. You'll see some similar things. You may also see a few things that aren't covered in the example that I work here. And so definitely useful to your advantage to look at the examples in the book. But let's try this one. Again, we're gonna say we've got a factor safety on ultimate strength of 2.0 is required. All right, so that's our required factor of safety. And we want to find the required cross-sectional area of member, I think BC, and also the minimum diameters of the pins at 2 points, A and B. And we're told the material, and all of this is made out of the same material. Fairly common, you might see the bars or beams or members may not be made out of the same material as the pins, but for simplicity here, we're going to say it's all made out of the same material. And this particular material has an ultimate normal stress of 6 KSI and an ultimate shear stress of 8 KSI. All right. Now I'm going to draw the picture in just a second, but one thing I wanted to mention before I drew the picture, I found this problem in a different book, but so that's where I got these numbers from. And in the next chapter 2 and 3, we'll be discussing more about material properties. I have no idea what this material is. It's a very strange material. The normal ultimate strength of the material is almost always much higher than the ultimate shear stress is. Almost all normal materials are going to fail at a lower shear stress than they would a normal stress. So I have no idea if this is some weird exotic material that whoever did this problem, or they just randomly made up numbers. I don't know. But I did want to point that out that sometime later this week, you might think back to this problem and think, well, those are strange values. Anyway, so let me draw the picture. We got 2 bars that are pinned together. We've got a horizontal member here. It has a pin support at this end, we'll call A. Here at B is where the 2 members are pinned together. And it goes up here and it's got a pin support at C. This angle is 60 degrees. We've got 2 applied forces, both 1,500 pounds. And they're acting on that horizontal member AB. And some dimensions. So the first 1,500 pounds is 2 feet from the end A, and then 4 feet you got the other 1,500 pounds, and then 2 feet from there to the end of that bar B. And we're given a picture showing what these 2 pin joints at A and B look like. So this pin support at A, it looks something like this. And then you've got the member AB, and it's got a pin through it. Now over here at B, our member AB here has kind of a forked end. And then you got member BC goes between those 2 forks, and then you got a pin through there. All right, so again, just a second to make sure the picture is up, is clear. And one observation, if you hadn't figured out, is going to be very important. You've got to be able to recognize 2 force members. So just make a note here. This member BC, that's a 2 force member. Right, pinned at each end. No forces applied in between. So I know the force in that member is going to be going same direction as a straight line through those 2 points. Other thing, just an observation, we discussed single shear and double shear previously. Looking at the way these 2 joints are constructed, I would hope, and we'll see next Monday, but you should be able to, if you look at A here, this is what we call single shear. All right, so the shear force V is going to be equal to whatever the force is in that member. And here at B, right? This is double shear. Right? There, the shear force V is going to be half of whatever the force on that pin at B is. And that'll come into play here shortly. But first, we've got to calculate what the reactions are at this pin at A. And we need to know what the force is in BC, because that's going to be the force acting at that pin B. Plus, we're trying to get the required cross-sectional area BC. So we need the force in BC, and we need to know what the force is at the pins. So if we look at our free body diagram, here at A, we've got a pin support. Going to have a horizontal vertical reaction forces. We'll call them AX and AY. Got our two applied loads, 1,500 pounds, 1,500 pounds. And here at B, we're going to have force BC. It's going to act same direction BC is. It's at 60 degrees. Now you can assume it's going either direction, going up to the right or down to the left. But here I'm just using a little common sense looking at it. If these two 1,500-pound forces are pushing down as the force in BC's got to be going up. That's what's holding it up. So, but it's okay if you assume the other direction. You'll get an answer that's negative, telling you its direction is opposite what you assume. So we're going to take our free body diagram here, which again, this is 2 feet, 4 feet, 2 feet. And we need to find those three forces. So I would start by summing the moments about A. Set that equal to 0. Now over here, right, if we break that up into horizontal vertical components, by multiplying by sine or cosine of 60, the horizontal component does not cause a moment. It goes through point A. Just the vertical component does. So we have force BC sine of 60 times, what's that, 8 feet? It's the total length. And that's a positive moment. The two 1,500-pound forces are causing clockwise moments. So minus 1,500 times 2, minus 1,500 times 6. And that's got to be 0. And so from that, we can get force BC. I got 1,732.1 pounds. So that's the force in BC. We need our support reaction, AX and AY. Sum the forces in the X and Y direction. And we should be able to calculate what AX and AY are. So in the X direction, I assumed AX is going to the left, or to the right, sorry. This component is going to the right, so plus 1732.1 times cosine of 60. And those are only two forces in the X direction. Solve for AX. It's obviously going to be negative. I got 866 pounds. Again, the negative is just telling me it's going opposite what I assumed, which you'll see later for this problem doesn't matter. But it would be going to the left. And in the Y direction, we got AY going up, 1,500, 1,500 going down. And then the vertical component, force BC going up, 1732.1 sine of 60. Well, that's got to be 0. Solve for AY. And I got 1,500 pounds. It's going up. So at this point, we've done nothing but stacks. drew a free body diagram, calculate our support reactions and the force in bar BC. All right, everybody with me at this point? Any questions before we get into actually designing and determining how big these members need to be? All right, so let's start with BC. So if we're talking about bar BC, I know, right, sigma is P over A, right? The normal stress in BC is going to be whatever the force in BC is over the area. Right, but here's where we got to use our factor of safety and our material properties to determine what the maximum stress here can be. Right? I got a factor of safety of 2. The ultimate strength of that material is 6. So what does that mean if our factor of safety, ultimate is 2, our ultimate strength of that material is 6 KSI. What's our allowable stress? Somebody want to tell me?
3.
3.
3.
Okay, it'd be 3. So again, take 6 divided by 2 is 3 KSI. So in order to maintain a factor of safety of 2, I cannot have a stress larger than 3 KSI. So that's what we're going to set our stress equal to. It's 3 KSI. Now be careful with your units. I mean, this is KSI. Our force that we've got is in pounds. So we got to do one of 2 things. We either got to convert the KSI to PSI or convert the pounds to kips. Either way works, but you got to do one or the other. I don't know. I go see 3,000 PSI would be equal to 1,732.1 pounds divided by the area. So just solve, get the area. So take 1,732 divided by 3,000, and it comes out to be just over half an inch squared. So I got 0.577 inches squared. So that's what the cross-sectional area of BC has to be, at least that big. Right? That would be the minimum. Anything bigger than that, that's fine. We're going to have a factor of safety bigger than 2. But that would be the minimum cross-sectional area so that we have a factor of safety on ultimate strength of at least 2. All right. Any question? Now we got that. All right, well then let's move along to our pins. Now before we get to each pin, we're going to do the same kind of thing. We got a factor of safety on ultimate strength of 2.0. If we go back up, our ultimate strength of this material is 8 KSI. So that tells me the allowable shear stress is 4 KSI. Take our ultimate strength, divide by the factor of safety. That's the maximum stress that these pins can experience. Now, before we look at each, well, let's just go ahead. We'll look at pin A first. It doesn't matter which one we did first. And we did a problem like this the other day. I have AX and I have AY. I actually need to know what that resultant force is. Right? We can't base it on just the X or Y component. Right? I need the resultant force. I need to take AX squared plus AY squared, sum those together, take the square root. So if we take 866 squared plus 1,500 squared, I got 1,732 pounds. So that's the resultant force acting here at this pin at A. And we said it was single shear. So if it's single shear, right, that shear force V is going to be equal to FA. So back up here, this picture, here's FA. The shear force in that pin has got to be equal to FA. So just like we did previously, I know the shear stress is going to be whatever that shear force V is divided by the area. So we're going to set our allowable, our shear stress equal to the allowable, which was 4. So this is, again, we either got to convert to PSI or the force in kip. So I'm going to go PSI instead of 4 KSI. V is 1,732 pounds. And the cross-sectional area, again, if it's a pin, the area of a circle, pi over 4 d squared. So pi over 4 times the diameter squared. So we take that and solve for dA. I got 0.743 inches. Right. That is the minimum diameter of pin A, so that we have a factor safety of at least 2 on the ultimate strain. Now, just a sort of side note, if we were designing this in real life, we could, call up, some manufacturer and say, I need a 0.743 inch diameter bolt or pin, and we'd pay probably 10 times what we would if we just went and bought a 3/4 inch diameter pin off the shelf, right? So again, this is just the minimum. We don't always necessarily have to, use that. Anything larger than that would be even better. Any question how we got the diameter for pin A? All right, so I'm assuming if everybody can stop me, if I run out of space, I got to get a new sheet of paper. Everybody's good with. All right. So we just got one pin left to do, right? We got to do pin B, which we said it was double shear, right? We had this, draw the picture here. All right, so this would be the force in BC. And so here, the shear force V is going to be half of that. So here V is going to be half of force BC. All right, everybody with me on the fact that that's in double shear? So I know tau, shear stress, is going to be whatever the shear force is divided by that area. Just like we did for pin A, set our shear stress here equal to the allowable, which was 4 KSI or 4,000 PSI. The shear force V, this was what, 1,732.1 pounds, I believe. And then divide that by the area is pi over 4 d squared. Here we're talking about the diameter of pin BC. Solve for the pin, and I got 0.53 inches. Again, that's the minimum diameter. Anything smaller than that, we don't have a factor safety of 2. we exceed our allowable stress of 4 KSI. Anything bigger than that, we're good. Now, I know we're out of time here, so I'm gonna wrap this up in like a minute. But one thing I wanted to point out to you, emphasize, this example we just worked. Starting from where we did, doing our statics, getting our reactions, getting the normal stress, shear stress in the pins, factors of safety. This one problem pretty much included everything that we have done so far. And it didn't have anything about bearing stress that we talked about. But otherwise, it pretty much included everything that we've done to this point. So, there's something to digest that if you can work this problem and you understand everything we did here, then pretty much from the beginning of class till now, you're in good shape. And don't be surprised to see something similar to this on the test next Monday. Like I said, this one problem pretty much covered everything we've done so far. So, last chance, any questions about this problem specifically, or I suppose anything in general? No other questions about anything at this point? All right, so I'm going to stop recording here in just a second. Any of you, if you have questions about anything, you want to stick around, I'll wait a minute or two after I turn the recording off, and we can talk about anything that you want to. But I am now turning the recorder off.